We're going to get started with Jarrett Revels, who's going to talk about cassette.
That's right. Yeah, so as Eric said, my name is Jarrett. I work at MIT, and normally I'm doing things like benchmarking and automatic differentiation, but for the past year of my life, I've been diving deep into Julia's compiler to try to build this weird tool called Cassette, and that's what I'm going to be telling you about. First things first, so let's... Oh, nice, already on the way. See, this is exactly what working on cassette is like. Fingers crossed. Yeah. Right? I think that's what we're attempting to do. We're just restarting the converter.
Reboot this guy, yeah.
Do I get this?
You do. Yeah, you're all good.
Does that mean that I can go over and be like, oh no? Damn. I don't think it's the computer that's the problem. Aha! Woo! Thank you. Hi. So, first things first. This is long overdue. It's not really a good JuliaCon talk if you don't make a release, right? We're going to do that. We're not going to go with 1.0. That would be too aggressive, I think. There are too many 1.0s at this conference already. Okay. Juan Pablo got the marketing. There you go. And then I'm just assuming that Adabot will take over from there. Thank you. All right. Okay, cool. So we did that part. And now let's do the rest. So actually, I kind of want to apologize in advance. The approach for this talk, I think, will be trial by fire. So I'm going to be just flooding you with examples and explaining maybe a little bit of them. We'll see how it goes. So I think I'll first talk about maybe the problem domain that motivated me to start working on this kind of stuff. So I basically started to notice after working on a lot of different things in Julia that many Julia packages are trying to fit a square peg into a round hole. And what I mean by this is that many Julia packages are trying to use method overloading to implement some form of non-standard interpretation of Julia programs. So specifically in AD, we have this classic example of a dual number, which is just a wrapper around a value that also keeps track of a derivative value. And then you overload various mathematical primitives on this wrapper type in order to compute derivatives and propagate them using the normal kind of chain rule And so this is a case where we use method overloading to implement a form of non-standard interpretation where we're reinterpreting a Julia program into the Julia program that calculates the original's derivative. So you actually see this kind of technique happen all over the place. So David Sanders has a wonderful package called interval arithmetic that does a very similar thing, except instead of trying to calculate a derivative, he's using this approach to calculate rigorous bounds on a program's output. And then more generally, you can just use this to derive a call trace that represents your Julia program in some other way that you can then do kind of higher level optimizations or transformations on. And so this is maybe becoming a more common technique because it's easier to manipulate these sorts of traces than it is to manipulate Julia code directly usually. So this approach is actually a pretty standard approach. It's not unique to the Julia ecosystem. It's very common in other languages that support polymorphism and generic programming. Julia, though, is actually really, really good at this, mainly because, I think, because it provides a multiple dispatch implementation right out of the box. And you're normally doing things in other languages basically to try to get to this point where Julia already has it for free. And so I think that's allowed us to really push the boundaries and explore the space made available to people by this approach. And I think it's attracted a lot of state-of-the-art implementations that currently exist in Julia that people are using. But I also think that the approach stinks. So once you do this enough, you realize that this approach is easily thwarted by type constraints in user code. And this is where most of the issues in the forward diff repository come from, is people saying, well, I can't propagate a dual number into this function where I hard-coded my variable to only be a vector of float 64, right? So when you start seeing enough of these issues, you start to ask yourself as an implementer, okay, I obviously don't support all of Julia, right? I don't support these hard-coded forms of Julia, and that's valid Julia code. So what weird subset of Julia do I support? And you ask yourself that as an implementer, and it can be quite difficult to answer. But if you're a user, it's borderline impossible, I think, to answer this question or to really understand answers to this question unless you have a developer-level knowledge of the package you're working with, which is obviously unscalable, right? So I think that's a huge problem, and it's probably one of the main ones that I care about. Another important thing is that for some types of applications, maybe you want to think about and analyze properties of programs, specifically Julia programs, where the language kind of mechanisms or properties that you want to analyze are not actually available to you simply via intercepting it with method overloading. So things like control flow, literals, bindings. Sometimes maybe you'll want to analyze a whole program and analyze calls in a program that won't even necessarily be executed in a pass. And so in that case, you're out of luck if you're using something like operator overloading. So finally, if you ever had to work in this regime for long enough, you start to realize that composing these implementations that use this approach, especially if they're not working on numeric types, but they're working on things which aren't efficiently convertible to one another, for which Julia doesn't really have a good promotion mechanism like arrays, you start to run into crazy method ambiguity problems that require pretty hacky solutions in order to solve, and it's no fun. So my whole point with making Cassette originally was to solve these kinds of problems, or to come up with an approach that's different at least. I think it's expanded a bit beyond that at this point, but yeah, I guess you can see for yourself. So most of the rest of the talk I think will just be giving some examples, and we'll see how far we get. So the first one is just a simple logging example using Cassette. So the kind of high-level way Cassette's API is arranged is that you define an execution context that is relevant to your application or what you're trying to accomplish, and then you can execute programs within that context. And Cassette essentially instruments your programs with all these different points of overloadability where you can overload things that are running in your context with respect to your context and kind of imbue them with contextual behaviors. So one example of this is the Cassette's prehook function. So basically, Cassette instruments your program when you're running it in a context to always have this prehook function get called before every method invocation in the program. And so what we're doing, by default it does nothing, but what we're doing here is we're overloading this with respect to our context, which we defined called print context, just to print out the call. And so then we execute a very simple program, just computing 1/2, with our print context. And so Cassette's pun for this, it's the one remaining audio pun in Cassette, and I will not give it up, it's overdub. So we're overdubbing this program with respect to this context, and as you can see, it prints things out quite nicely and gives us the correct result. So since prehook is a normal Julia function, it can utilize multiple dispatch in kind of the normal way you would hope. And so I have an example here which kind of shows that happening, and also it kind of shows that you can associate arbitrary metadata with context instances. So what I'm doing here is I'm defining a different context with a different prehook, and the whole game we're going to try to play here is we want to count the number of calls that occur in a trace where the first argument to the call is of some type, right? It's kind of a very contrived example. But how we accomplish it is we define some structure we're going to use as metadata. We parameterize it with a type, and we define this prehook definition here where we use the parameterized type to match the type of the argument that we want to check for and increment our counter based on. And then now we've basically parameterized this entire contextual execution environment with respect to this type, and we can do different things. So for here, for example, oh, this is quite annoying, isn't it? Well, anyway, so here, for example, we're going to run the same program that we ran before, and we're going to check for arguments where the first argument is a data type. And then if you run the program, it then increments the counter, and it's 2. And if you check the div function, you'll see that that's correct. So anyway, so more practical kind of example. So people wish to use Cassette to do some of the trickier, smaller tasks inside of GPU cross-compilation, transpilation. So one problem that they have when doing this type of stuff is that people's code, which they'll want to try to compile for the GPU, will be utilizing these CPU-specific functions. So like in base Julia, we provide CPU-based implementations for exp and tanh, for example. And people cross-compiling Julia code to the GPU want to easily swap those out for GPU-specific mathematical primitives. So here's an example where we're using Cassette to do that. So instead of using a prehook, we're going to overload the actual method Cassette uses to execute code. And so normally this defaults to just, okay, I'm just going to trace into it further. But here we're saying, no, don't trace into it. We've defined a more specific method. And for this method, we wish to, for example, replace base.tanh with CUDA natives tanh, and the same for exp. So on the right-hand side here, we have some example code where this might be useful. And we can simply execute this code in a GPU context to get the desired result. So there is one thing happening here that we actually might want to be fixing, which we're not fixing just by doing this, and that is the idea that there are all these kind of 64-bit literals floating around. So one other thing that the GPU people want to do is they want to translate these into 32-bit literals just for performance sake on the GPU. So you can't really do that via method overloading in any sense. So Cassette provides this mechanism for you to just provide an arbitrary Julia function and apply it as a compiler pass at compile time over every method body that is encountered in your execution trace. And so we can, this is kind of like, this is maybe using a cannon where we maybe should have used a scalpel or something. But so we're using this right here to take every 64-bit literal in some given method body and convert it to a 32-bit literal if it's possible to do so. And that's what this pass function does. It's just a normal Julia function where it takes in a context type, a method signature, and a method body. This is like a code info object. And then it runs the pass it wants to run, and then it returns the method body. And so that's the method body that then Julia will see and mess around with. Thanks. So you can actually execute this by just providing the pass to the context when you instantiate the context and then running it. So that does that. So this is one of my favorite kind of examples, simply because it shows how much you can accomplish with a very small amount of code. So here, what we're doing is we're essentially defining a context where when you execute a program within the context, you accumulate a nested trace of the program. And I don't know how much time I really have to go into the implementation here. But suffice to say, it just recurses into the program, and every time it sees anything, it pushes it onto the trace that's being accumulated, that's being stored in the contextual metadata. And I think the point here is that it's a very small amount of code, and now all of a sudden you can arbitrarily kind of trace into Julia programs and get out like a rich nested representation of the program that you can then do whatever you want with. So I have another example. So this is new if you happen to have seen my previous examples in a previous talk. This one's new. So this was motivated by a kind of challenge given to me by Mike Innes. He was asking basically how to implement this kind of thing in Cassette. And I think it's a very good like pedagogical example, and also might be useful in the future as well. So this is basically our goal here is going to be to, given a Julia function, slice out all of the calls that are like IO calls. So for example, println calls. Slice out all of those calls and then run the program basically without them. And then at the end, return both the output of the program and a callback that then will actually execute the calls that we stripped out. So if you're familiar with continuations in other languages, this is basically asking for a like somewhat limited continuation implementation. So essentially, just to be clear, what we want to do is we want to be able to run this add function, right? And normally it prints out this stuff and then returns the result. And we want to be able, we want to have it return the result without printing out anything, and then give us another function that we can call later to do all the printing that we stripped out. Okay, so this is quite easy to do in a naive way using Cassette's contextual dispatch interface, using these kind of execute methods that we can just overload. Where we simply overload a contextual primitive for println, and then when we encounter it, we update a trace local closure that's just being stored in the contextual metadata. And then at the end, we basically can, so as you can see here, we can simply run this program now in our context, and then it doesn't print out, right, the things that we stripped out. Because we defined this to actually be nothing as it's running, and instead you can execute the print statements later by just calling the closure that we computed. So it's a pretty weird example, but it's very cool. And so one of the key things here is that this implementation has a couple limitations, right? So we explicitly have this barrier to inference in the field type of the callback struct. So when we're constructing this closure, we're basically saying, okay, you can't really infer this, so the compiler won't even try to, which is maybe nice for the compiler, right? But might not be so nice for you if you wanted to infer. Another limitation here is that this really only works at a level of intercepting method calls still. Right? So this only really works at the level of saying, okay, I want to strip out println calls. But what if you want to, say, strip out println calls and you want to strip out any of the construction code that constructs an argument to a println call? Like maybe you want to take the whole statement and remove that, right? You can't just overload string because you have no idea where maybe naively you would try to, but then like what if somebody actually used a string in a computation? It requires some kind of linear dependence analysis that you need some extra scope information to really achieve. So this is a place where you can use Cassette's contextual dispatch interface to implement something, but maybe you actually want to write a real compiler pass. And so what type of compiler pass maybe do we want to write? Well, it's this one. We essentially want to take our original function, and if this was our original function, what we want our pass to do is we want it to basically introduce a new callback variable, and then we're going to be passing that around and updating that instead of updating this mutable state. The reason why we're doing this, right, is because Julia's type inference can track through updates to variable bindings, right? So this is essentially doing the same thing, but by having doing it at a pass level, we're able to achieve something that we weren't really able to achieve without it, right? Furthermore, this would allow you, because you have all the information you need to do the analysis, you could kind of expand what this callback is capturing at any given point in time. And so there's an implementation of this pass. I'm not going to go over it because it's actually kind of complicated, but this is in the cassette documentation, and if you want to dig deep, you can kind of read about that. And then this is just showing it working, and as you can see, it returns, because of the pass that we implemented, this function now returns the callback with the result, and we can just call the callback, right? So now that I've kind of shown you a bunch of crazy examples, maybe I should explain a little bit about how this is working. So you can think of overdub as basically whenever it sees any method invocation in code that's being contextually executed, it replaces that method invocation with these statements. And so here we basically see where prehook is now getting called, execute is getting called, posthook, which I didn't talk about, but it's basically like prehook, right, is getting called. And you can see the interaction between execute and overdub and how cassette is doing its recursive tracing into, like further into your code if, for example, you try to execute something and it's an auto primitive. Once again, this is explained in detail in the documentation, but just to give you a sense of what this looks like and maybe motivate you to play around for yourself, you can just mess around with code lowered to kind of see what cassette will do to your code. So here we have our simple 1/2 calculation that we were doing before, and it's nice because it only has like 3 method calls in it, right? So if we look at the code lowered for overdub, it's quite a bit uglier, but you can see those calls where they got replaced. So there's the float x call, there's the float y call, and there's the div call. And it's worth noting too that when cassette is applying your pass that you provided, if you provided it with a compiler pass to run, it's executing it on this code. And then it's applying its own transformation to get to here. So yeah, so that's a pretty important detail. Okay, the last thing we're going to talk about is kind of something that maybe actually addresses what I was talking about at the beginning of the talk with non-standard interpretation, dual numbers and intervals, et cetera, et cetera. And that's Cassette's contextual tagging system. So basically what this is Cassette supports tagging arbitrary Julia values with respect to a context and optionally associating some metadata with those values. And then you can essentially use those values as arguments to your overdubbed program, and they will propagate throughout the program like fairly arbitrarily, regardless of whether there are like dispatch or structural type constraints or whether they flow through mutable like global state. Like it's pretty arbitrary. So this essentially so it basically allows you to do the dual number thing, but through cassette, and you get a lot of cool features that way, which we'll see. So I think the first thing to go over is being able to compute the identity. So that's a pretty tough one if it's implemented like this. So essentially, yeah, so it's just an identity function, but implemented in such a way that would like thwart trying to propagate something like a dual number through it, because it's actually has all these like hidden type constraints in it, right? And specifically, it's not even really an identity function. It's more of like a convert float64 function, because we have this float64 array that we're going to be pushing our value into at one point and then popping it out from. So here we're just going to be using just integers, right, to pass through. And what our goal will be is to pass through 1 and have it go all the way through, and then pass in 2 as the metadata and have that also propagate all the way through alongside 1. So here's how we do that. We, as per usual, we define a context. And then we overload this special function called metadata type in cassette to essentially tell cassette what type of metadata we'll be associating with what types of values. So this essentially allows cassette, this is basically an optional optimization. It allows cassette to efficiently allocate memory on the stack or on the heap, wherever for the type of metadata that you're going to be propagating through. So you could pessimistically just say any, and then you could put any metadata, but then your program would probably be slow because it would have to allocate a lot of any memory. So, we tell cassette this, and then we construct a context, an instance of our context with tagging enabled for the function that we're going to be tracing through. We tag the value with respect to the context and associate our metadata with it. And then we overdub the thing and pass in our tag value as the argument. And as you can see, so Cassette's API for extracting the value from a tagged thing is untagged with respect to the context, and it triple equals basically what we wanted it to. And the same for the metadata. And so there's an interesting interaction that's worth mentioning here with this metadata being converted also to a float, right? And that has to happen because of this constraint that we defined. So we said, right, if you're a float64, then your metadata type has to be float64. That's what we were saying with this. We were basically defining this invariant. And because the original function converts it to a float64, then our metadata then gets converted to a float64, right? It's just a cool little interaction between Julia and cassette in this function. So, finally, I want to just show off a very simple forward mode AD, just scalar to scalar proof of concept, and kind of show the version of like cassette dual numbers and kind of what it buys you compared to doing just normal dual numbers in Julia. So the way to implement cassette dual numbers, I guess, is to, of course, define a context. And then just for convenience sake, we're going to define this type alias. All this allows us to do is more easily dispatch on this tag type that's associated with the context that we'll need to dispatch on. We define our metadata type constraint that we defined earlier. We have this kind of utility convenience function for getting a derivative out from a value, assuming it has a derivative attached to it. Otherwise, it just returns 0. And then we have our kind of one function API here, which is the derivative operator. And you see it's just a wrapper around constructing a context that's tagged with respect to the function, and then executing your function inside of that context, and then returning the derivative of the result. So here we see an example of doing the type of method overloading you'd be doing on a dual number, right? But we're doing it via cassette's execute function, and we're doing it on this tagged thing. So basically, there's not really much going on here. It's pretty boilerplatey, actually. And it'd probably be something you would actually just generate via metaprogramming if you were really implementing a package that did this. But one important thing to note is just that we have a dispatch constraint here that basically specifies that these tags have to have the same type, and that essentially buys you a lot of safety with respect to nested differentiation or nested metadata propagation in general. So yeah, it's really important. We'll see why. So yep, so you can define times and plus as well. Not super interesting if you've ever taken a first year calculus course. So that's all we need, and now we can differentiate stuff. And not only can we differentiate, sine and differentiate sine times cosine and all of that nice stuff, but we can also do nested differentiation. And many of you probably don't think this is interesting, but I find this extremely interesting because if you did a naive dual number implementation and wrote this program, it would give you the wrong result silently. Because what would happen is the metadata associated with your values at any given point would actually get confused between the inner differentiation and the outer differentiation. This is a problem known as perturbation confusion. It affects a lot of AD tools, and it's very kind of scary as an AD implementer to think that somebody's derivatives are going to be totally silently wrong, right? So if we use cassette, we avoid this by construction. So cassette is doing a thing internally that's pretty tricky with managing these tag types. And as long as we use cassette's API and do the correct thing with respect to overloading with respect to the tags, then we're good, and it will be all nice and safe. So the other thing we can do is we can differentiate right through that foobar identity function we defined earlier, which is something that you definitely couldn't do with a normal dual number implementation. And then finally, we're differentiating through this function, which I haven't showed you, which is just a really weird implementation of some x times some y. And this is maybe, being able to do this is maybe the culmination, I think, of what I've been trying to do with Cassette the whole time I've been implementing it. So this function looks like this. It's pretty screwed up. This is one of those things where you're like, man, nobody would ever write this in practice, but then people open up issues on the fordiff repository where people are writing this in practice. And it was basically my attempt to create like a pathological test case for cassette-based automatic differentiation. And I'm not even going to, this is in the tests, so this is like, cassette test will fail if it can't do this. Feel free to read and cry at your leisure with this one. So I'm basically out of time. I'd like to thank a lot of different people. So Juan Pablo is my boss at MIT ORC, and it's huge appreciation to him for supporting me throughout this project. My lab mates at CSAIL, and Valentin, who is also a conference organizer. The whole compiler team at Julia Computing, without which this would never have gotten released, and Jameson Nash specifically, without which this never even would have happened or started probably. So I'd like to thank all the people that have been opening up issues and kind of helping me think through the weird ideas that crop up when you have the kind of abilities that you get from Cassette, and then all of you people for attending my talk, and the conference organizers. Thank you. Any questions? I bet there are.
What's the cost, especially in compile time, that's associated with going on the whole call stack and rewriting everything?
The cost is high. So the compile time cost is fairly high. It's not insurmountably high. It's for example, not too much worse than forward diffs dual numbers, which that's not necessarily a good thing because forward diffs dual numbers have been known to really, really stress out the compiler. You didn't ask about the runtime cost, but I'm going to answer about that too, because there is some. So currently, Cassette, if you're not using the tagging system, things mostly infer well. Type inference can get through it normally just fine. Code gen and optimization could be a little bit stronger, and so sometimes you'll emit code that has allocations in it when it shouldn't. If it doesn't have allocations and it infers well, the overhead that I've seen at runtime is about 2 to 4x, which is actually way smaller than I thought it would be. But I mean, a lot of work in the design of the package has gone into this idea that theoretically, with the right compiler optimizations, we can get it down to no overhead, right? So a lot of that work has happened and is planned. With the tagging system specifically, it's extremely slow because it relies on several compiler optimizations. It relies heavily on several compiler optimizations that don't exist yet. They're planned, but they don't exist yet. So I think the goal with the release was to get things working, and then if people start using it, then Jeff will be like, I have to make this fast now. So that would be good. Yeah.
So if I want to rewrite something just a few levels deep, but that then calls in a big chunk of user code, it still has to descend down all the way, right? But it will not
it doesn't. No. So it doesn't. Once you overload this execute function, it stops tracing through that section of it doesn't descend any further through that section of the call tree. It will through other parts, but you can actually be quite selective with this using Julia's multiple dispatch to try to decide where you want to trace through and where you don't. Yeah. No problem.
I wanted to ask about really beautiful work. It's an amazingly powerful package. So I wanted to ask about to what extent do you think it is now or will be possible to do higher order analysis of programs via cassette, or if one should just go about manually inspecting the AST. And what I'm thinking about, for instance, is A lot of times, someone will write an algorithm, and if you pass it a small amount of data, it completes extremely quickly. But if you pass it a very large data set, you'd be waiting an hour. And then when you transition to that, I've been waiting a while, suddenly people can start getting interested in having like some kind of progress meter or something
Oh, yeah.
like that, right?
Yeah.
If you wanted to automatically instrument the code to insert a progress meter, that's something that the caller might know would be desirable, and the program author might not have anticipated. So
Right.
something like cassette seems extremely attractive for doing that.
Yeah.
The main point is you want to be inserting the progress reports in the right spot. You might not want to put it inside the innermost loop of your function.
Right.
You might want to have it fire episodically or something.
So I think the normal way to do something like that is to have a context with some metadata associated with it that is essentially the configuration state for the context. And then when you're overloading your pre-hook or your post-hook or all these instrumentation methods that I call Cassette's contextual dispatch interface, when you're overloading these contextual dispatch methods, basically query your configuration state to decide, do I descend further or not based on what the user told me when they invoked my instrumentation library or whatever.
But does the user have to understand the
Code that he or she is instrumenting, or can you write a generic instrumenter that would
A generic instrumenter for
Oh,
sure.
wow.
So like the whole term that I've been throwing around is it works on cassette-unaware Julia code, and that's like the huge point of it, right? So
Very cool.
thank you. Anything else? Okie dokie.
All right, let's thank Jared again.
Thanks.